Welcome, ladies and gentlemen. My name is Mark Schinke. I'm working as a project manager for CIMAC. Today, it's my pleasure to welcome all of you to the last of our Tech Talk special in the series that went on through 2022. We are all looking forward to the Congress going on next year in Busan already, but today it's our pleasure to hear 3 different presentations about engine components. Today, Mr. Stein from Robert Bosch, Mr. Koppo from OMT, and Mr. Hager from Mibo Gleitlager will hold a presentation. Today's moderator is going to be Mr. Engelmeyer. Before we can start, I, as usual, have to make some legal hints. With the CIMAC Tech-Talks specials, we would like to offer a platform for exchange. The presentations are an information offer for the respective author and or their company, and thus do not necessarily reflect CIMAC's opinion. Please be aware that this session will be recorded so that you can later on have access to it on YouTube in case one of your colleagues missed it. And please type your questions in the chat. Feel free to do so during the presentations already so that our moderator can review them and afterwards ask them to the speaker. With that being said, I'd like to hand over the voice to Mr. Engelmeyer to guide us through today's Tech Talk special.
Thank you, Mr. Hinke. Good afternoon and very warm welcome also from my side. My name is Michael Engelmeyer and I'm from the Large Engines Competence Center. I'm responsible for an area with a quite similar name to today's topic. It is the engine components and sensorics. And as Mr. Schinke said, we will have 3 speakers today and start with Mr. Jens Olaf Stein from Robert Bosch AG. And his speech is about fuel injection and emission systems for liquid and gaseous bio and e-based fuels for large engines. Mr. Stein, please start your presentation.
Thank you very much for the introduction. Let's see. Just to put this away. I would not like to close it, so let's hope that it works. Here. Perfect. So I hope you can see my screen in a few seconds. Is it visible? Are you able to see my screen? Just as a
I think we see your second screen currently.
Okay, then I have to just change this. So now you should see it, right?
I think we still see your presentation mode and not the presentation in full screen. Now it's in full screen. Now it's correct.
Now it's perfect. Okay, there's maybe a little bit time needed until it switches over. Okay, perfect. That means we have now the technique under control. So good afternoon, good morning all around the world. Thank you for participation here to my lecture. It is about injection technologies for alternative fuels. I would start with the future demands and the technologies, coming from that to the combustion system of the large engines, and then to the solutions from the injection systems point of view. At the end, I would like to sum up and give also a short conclusion from our point of view. So looking towards the mobility trends and the demands in the future, you see here on the left side, in principle, the global demand for the passenger car transport by modes, and on the right side, the same by freight. It is quite well visible that there is a huge increase by about 3 times from 2015 to 2050. The biggest increase will be in the freight transport, and in particular sea and waterway. And the reasons for that, of course, the global supply chains, that's important, and the overall growth in the GDP. So this means there's huge demand for energy, and from that point of view, of course, also for the large engine segment. So this means on the other side, when we focus on CO2, there is, of course, a lot of things to do. To avoid that, with this increase, we have also the same situation for the CO2. And knowing that we have already the situation that we would like to keep, and if we would like to keep the CO2 under control, we have to do even more than currently is initiated. This means there's a huge task in front of us. Coming now a little bit deeper into the large engine segment as well. It is in principle separated into 4 subsegments. We have the gensets, we have the maritime, we have the locomotives or railways, and we have also mining. On the left side, you see here in this diagram the today's situation, and on the right side, the future situation as predicted. The diagrams gives you an overview about the fuel supply on the y-axis. It could be via a network, it could be via local storage, or of course also via the onboard storage if it's mobile applications. And on the x-axis, you see the mileage or the utilization versus the time. These are important parameters at the end to conclude on the fuel. I will come to that a little bit later. You see on the left side, the current situation in blue is, of course, that we have the ICE, mainly fired with diesel or derivatives of diesel, and also already natural gas. When it comes to the future on the right side, there is a certain change in the technology. You see we are talking marked in green about new fuels. This kind of fuels are characterized in principle that they have either an improved ratio between the carbon and the hydrogen, or even that they are carbon free, which is the case, for example, for NH3 or for hydrogen. It could be also that we are talking about the standard fuels, but from another source, biofuel, for example, which reduces also CO2 already initially, or even that we have e-fuels. So that's in principle the situation what we are talking about when it comes from today towards the future and the large engine segment. And what is also seen here that there might be also the one or the other application with a fuel cell. What does it mean in principle from the point of view the future landscape for the fuel? So as an example, but I think this is quite valid also for the other subsegment, we are talking here about the maritime. You see on the right side the sailing pattern versus the sailing distance for several types of ships. And that's exactly the topic what we are talking about when it comes to the situation, what kind of fuel from this kind of diversity, what we focus in the future, will be the right one. It is not that easy because this kind of parameter which are important to decide of that. One is the use case, and you see that, for example, for the sea, for the ships, in principle, there's a huge variation, and it covers more or less all patterns what are in principle thinkable. So this means this is not that easy, and I will come to this a little bit later, to decide at the end what kind of fuel is the right one. Currently, we are talking about diesel fuel mainly, and that's it. But this kind of single solution is no longer possible in the future, and it makes it a little bit challenging. So how does it works towards the future? You see it on the left side in this kind of column diagram. It shows in principle from 2020 towards 2050 how the fuel types will be developing. 2020 means more or less currently we have the situation that all the fuels are in principle derivatives from diesel. When it comes already 10 years later to 2030, we see that there's already about, in this scenario, about 20% the new fuel types, which is in that case e-ammonia, LNG, and also certain kind of advanced biofuels. Additional 1 decade later in 2040, you see that already more than 50% is with the new fuels. This is due to, on the one side, further growth of the aforementioned fuels, as well as supplemented by hydrogen, e-ammonia, and even electricity. And in 2050, we see that most of the fuels are already this kind of new alternate fuels, which have less contribution towards the CO2, and only a very small amount is only the blue one, which means the diesel. So what does this mean in principle then from the decarbonization path for maritime? The right side shows in principle on the bottom the situation as it is today. We have the ICE with a diesel. There is a quick win already with biodiesel and methane, or mostly LNG. And then the next step will be the ICE with this kind of new fuels. It means we are talking about potentially ammonia, we are talking about hydrogen, and we are talking about also about methanol. There might be also the one or the other application already with a fuel cell. There are certain limits from today's point of view for the fuel cells, especially in the large engine range. The one is for the PEM, for example, that there are certain requirements from the cleanliness, and the other one is that the dynamic for the SOFC fuel cell is not that what is needed in all of the applications, so there are certain limitations. But based on this kind of scenario, you see already that it will come, and in principle there are a lot of scenarios available, and you see more or less the tendency is quite comparable. So the future is towards the new alternative fuels, but still with the ICE. Coming to the combustion system, you see again in blue on the bottom today's situation. We have the diesel, we have already natural gas. This means we have diffusive combustion, and we have premix combustion. And when it comes now to these new fuels, what you see here in green, there is a huge variation. It could be liquefied, it could be gas, and this kind of fuels you can burn either premixed or partly also under high pressure. So you see with that we have then for the PFI pressure levels for the injection system less than 10 bar. For direct low pressure injection, we are talking about pressure levels which are below 100 bar. And when it comes to the liquefied high pressure injection, at the bottom here we are talking currently about less than 600 bar. So on the right side there is in a qualitative manner shown in principle what is the engineering content and the efforts versus the experience and maturity level. So it's quite understandable that the current fuels, diesel, natural gas, which is quite comparable to the methane, is on the upper right side, which means it is already well known, very high experience, and the optimization is in principle in focus. There's no base work. In contrast to that, the ammonia is for the ICE a very new approach in principle. There were a few approaches in the past, but under completely different condition where there is no limit for emission, and there was no, let's say, challenge for the fuel consumption as well as the power. It's just that the engine worked. So from today's point of view, it looks, of course, much more challenging. It is unknown. This means there's a lot of basic works to be done. For methanol and for hydrogen, it's somehow in between, but also there, of course, is a lot of things to do for the combustion system, and not only the injection system. It means that we have to find a solution and an optimized approach at the end for the whole combustion system. So what is the approach for that? So when we do not know exactly the requirements, and that's the current situation shown on the left side. Again, we have the situation with the diesel, where the requirements, of course, quite well known. Lubricity as, let's say, certain parameters, and material compatibility is used here on the x-axis. It's, of course, for the diesel quite good. But when it comes to the new fuels, it is, of course, that we have to do a lot of investigation work on the combustion system, that we have at the end really defined the requirements as we have the situation currently for the diesel engine. This means that for the first samples of the injector is directly, of course, in contact with the combustion, and in principle it's one of the important components beside the whole combustion system, the air system, of course, and also the at the combustion chamber geometry. It plays under this kind of boundary condition to come here to a conclusion what kind of requirements we have for the new fuels. That we need here on the one side a robust solution already at the very beginning, that we have in principle the possibility to have a very good testing condition and reproducibility. And from the functionality point of view, it should be also the situation that these kind of injector samples have the potential to investigate all the parameters which are important, from the pressure, of course, also to the injection pattern. And that's very important. And you see here as an example, we have investigated 2 designs. And in that case here, you see that with the design 1, we have about 5 times longer lifetime, and that was exactly the design what we have selected for our AVLP, what I would like to show you and explain you a little bit later. But that's in principle a little bit the philosophy of our products here, that we try to start at the beginning with a product which has really very high potential from the functionality point of view, and what is kind of robust enough to do all this kind of investigation with a high accuracy and reproducibility. Coming now to the injection system itself, we have currently for all this kind of fuels, you see it here, it is ammonia, it could be gaseous or liquid. We have methanol, which is liquid. We have the hydrogen, which is gaseous. We have methane, which is gaseous. And we have then the possibility, what I have explained to you before, that we can use it either as a premixed combustion, which means we can use a port fuel injection, or we can have a direct low pressure injection, and it reaches until the high pressure injection for liquefied fuels. So you see then from the product point of view, in our portfolio we have for the port fuel injection for gaseous fuel already the large engine gas valve, which is series ready and already starting with the production for natural gas, and we qualified currently for these kind of new fuels, be it on the one side hydrogen or be it on the other side the ammonia. So when it comes then to the next step, direct injection, but on a low pressure level, which means, as I showed you before, less than 100 bar, we have our new injector, so-called AVLP, which means it is the alternative fuel injector low pressure. This is a kind of modularity which is able to inject on the one side liquefied fuel like methanol, but on the other side also hydrogen, which is a gaseous fuel, and it is also foreseen to inject NH3, means ammonia, and this could be either liquefied or gaseous. That's one of the important components for the future. I would like to show a little bit more details about that in a few minutes. Then you see the Avrp, so-called Avrp high pressure. This is the one which is for the diffusion combustion for liquefied fuels. We have here a concept available. We will do the detailed design in the next year, and samples will be available then as well. And finally, we have also our so-called LEECU, which is already available in the diesel version, based on the experience from the commercial vehicle segment, which has on the one side a very high robustness, on the other side perfect performance with a very good microcontroller, which is then adapted towards the requirements for large engine. And we would like to do here also the software development for this kind of alternative fuels for the future. Coming to the large engine gas valve here, you see we have in principle 2 sizes, the S size, small one, and the bigger one, the M size. This covers from 85 kilowatt per cylinder up to 600 kilowatt per cylinder roughly. And you see we have on the one side on the left shown our platform design, but beside that we have already solutions for several industrial interfaces where we have the capability to deliver as a drop-in replacement at this large engine gas valve. Coming to the Avrp modular concept, this is really a modularity which is based on the experience what we have not only from large engines but also from our automotive injection systems, where we concluded together with our colleagues at the end what is the best design for this kind of new fuels. You have seen before gaseous, liquefied. We are talking now no longer about a high pressure, about 1000 to 1200 bar. It is less pressure, but the challenge with the new fuel is more in the direction of the lubrication and also the aggressiveness against the surfaces. So this injector is in principle an injector with a direct needle drive, a solenoid injector. We have an outer open needle here, and it is ready for injection range from 10 to about 100 bar. We are able to cover in principle, depending on the engine type, from 150 kilowatt up to around 600 kilowatt with this injector type. And we have already run a highly accelerated lifetime test with this injector of about 500 hours, and the results are really overwhelming from the functional point of view at the end, as well from the robustness point of view and the wear behavior. So from that point of view, we have now already the second sample step ready at the end of this year, and customer samples will be available beginning of the next year. Also, we have already first results from the single cylinder engine, which shows also that this kind of injector is highly accurate from the injection pattern, as well as from the pressure wave behavior. It is really a very good spray behavior, which is able to achieve accordingly very good results from performance point of view as well as from emission point of view. Yeah, that's the one type, what I mentioned. The other one is the AFI so-called high pressure. This is the one for diffusion combustion, for methanol, or for potentially the NH3 liquefied phase. It is able to inject up to 600 bar. The base is in principle our so-called CRIM LE for the large engines, but we separate here the control area and the control fluid from the injected fluid. I told you already this kind of fluids are quite aggressive, so it makes sense to have here separation to ensure at the end that there is a high lifetime and the robustness available. And we have here the situation that we can inject up to 600 bar, maybe a little bit higher. It depends, as I showed you before, from the requirements from the engine, which have to come from the first investigations. And then we are able to cover 150 kilowatt per cylinder up to 600 kilowatt per cylinder with this injector type. As I mentioned before, this is already available as a concept. We do the final design now for the next year, and most probably the samples for the customer are foreseen at the end of the next year. So let me shortly summarize the current situation. So we can say that in principle, the technical solutions for the decarbonization of the large engine segments defined. We are talking about this kind of new fuels. The first step is in principle that we see an introduction of bio and paraffinic fuels, as well as biomethane. This is so-called the quick win. What I do not mention before, also ensure that our standard FIE for the diesel is ready until the beginning of next year for the use of the biodiesel, which is mainly in principle the validation. It is, of course, for this kind of validations where we have a specification, which means it's B20 and B30. But based on our initial investigation, it's pretty well that it is possible to use that, and therefore we have a solution for the first step and equivalents as well. Then the next step is hydrogen methanol. and potentially ammonia. Ammonia, from our point of view, is still a question about the laughing gases, which needs to be addressed and where we need a solution. But we do foresee it as well in our portfolio, as we have seen before. What is very clear from the initial investigation and even the, let's say, theory behind, we need not only a sophisticated injection system for this new fuel, it is also about an optimized combustion system, what is important to achieve the same performance and emission limitations as it is currently with the diesel engines. And what you have seen before, from Bosch point of view, our portfolio supports the complete decarbonization technologies with quite smart solution and robust design in principle, which ensures that the investigations are on a very efficient manner to be done. And finally, please allow me, from the perspective of an FIE supplier, it would be really great if there's a chance to consolidate with the fuel landscape, what we have seen before, and also with the combustion system in a quite early phase, because this would enable, of course, that we can work a little bit more focused, and this helps at the end also to achieve the final solution, of course, in a shorter time frame. So from that point of view, I would like to thank you very much for your attention, and I'm open for questions.
Thank you so much, Mr. Stein, for your very well structured presentation. And at this point, I want to encourage the audience to bring some questions up. And I can see there is a question from Nicole. Do you anticipate the need of lubrication enhancer for low lubricity fuels? What's your opinion on that?
Yeah, of course, what I mentioned. So what is in principle our design approach, that we separate on the one side the area which is important for the functionality, which means the solenoid, and also the guidance of the needle from the fuel, from the critical fuel, and that we have there a separate lubrication. This means in principle the critical fuel is only in contact with the needle seat area, and the important areas and sensible areas of the injector for the injector drive have a good lubrication via separate fluid included there. I hope that answers your question.
I guess yes, there is. I can see no other questions. I saw in your presentation one slide, so for the DI high pressure injector, is a concept, and you mentioned it. So it is right under development, and as the low pressure DI is, I guess, available. When do you think the high pressure will be available? I didn't get it before.
Yeah, sorry. Maybe I did not explain it so much in detail. So we have for the high pressure, so-called AVHP high pressure version for the alternative fuel, we have a concept which is based on the Quinn LE, which is the diesel injector. So this means also already in long time in series, pretty well designed, robust, and from the functional point of view also very good. And what we have to do now, based on this kind of concept, to come to the final design with certain simulation work at the end to make the final layout. And the plan for samples towards the customer is by end of next year, end of 2023.
Okay, thank you.
You're welcome.
I can see no more questions, and we are good on time. So thank you again for your presentation, and I will now introduce Marco. So next speech presentation will be done by Marco Coppo from OMT, and he will talk about powering a greener future. The OMT injector enables high pressure injection of ammonia and methanol. Marco, please.
Thank you very much, Miguel, and thank you everyone for attending this presentation. Can you all see the screen?
Yes, we do.
Yeah, perfect. So then I shall start. So thank you, Mr. Stein, for a very interesting presentation, which said already many of the the groundwork and the issues that any fuel injection equipment maker has to deal with new fuels. And this work they present today is, first of all, a work that we did in cooperation with the ADC. And so I would like to acknowledge also my co-author, Nicole Vermuth. And this is about trying to test injection technology in all possible ways with methanol and ammonia to understand, build knowledge to move in the graph that we saw in the previous presentation towards the known and reliable areas of the diagram compared to the all to discover one where we all started with these new fuels. And so today the issue is about how to, so this presentation is about how to design an injector for these new fuels. There are additional requirements that these new fuels pose to the development of these fuel systems, like we need to ensure safe handling, reliable equipment operation, and we also have to discover again how to make an efficient combustion of these fuels. And to all of this, of course, the fuel injection system is the most affected by this change of fuel. For example, we have increased need of safety measures due to toxicity, but also we have a higher risk of cavitation, seizure, corrosion, and on top of that, we have to deal with the low heating value of the fuel, which is less than half of the diesel on a mass basis. So we need to make the injectors bigger. We need more passage area to avoid having significant pressure drops in the equipment, and all of this, in a challenging location is in the head where normally the space is always insufficient for injection equipment. So we asked ourselves, how do we design a high pressure injector capable of reliably injecting methanol and ammonia, and which performance can we expect from a combustion of such fuels in a combustion engine? And finally, how do we optimize combustion of these fuels? So these were the main questions that we wanted to answer within this project that was done in partnership with ADC and also with ADM, which are here acknowledged. So now, if you have a look at the some features of an injector design, of course, stainless steel, we deem it necessary to make sure we don't have issues with corrosion, or we limit the issues with corrosion. We need to have hard metals for the control valve seats and fuel back pressure to reduce risk of cavitation erosion. Just to give you an idea, in this area highlighted here, which is where the control valve seat is located, and it's discharging fuel from rail pressure to tank. Without back pressure and without hard metals, after a few hours, the only piece of seat that remained is this triangle at the bottom. All the rest is completely eaten away with methanol. Conversely, applying 10 bar back pressure and hard metals in the same time frame, we could achieve still more or less perfect conditions of the seat. So there is a lot to play with materials and with injector requirements to make sure that we ensure the reliability, which is one of the main issues to deal with when changing these fuels. Further on, to avoid seizures, of course, moving elements running in low lubricity fuels need to have some coating that reduces the friction coefficient and prevents seizure, like DLC, which we apply to all the needles and pistons here. And also for sealing elastomeric elements, especially when testing different fuels in the same injector, the only compound that really does the trick for everything is FFKM, even though it's rather expensive. but otherwise you cannot get compatibility with everything that we wanted to test here. So regarding the hydraulic characteristics of this injector, we wanted to push the capability up to 1500 bar to explore the wide range of operation pressures. Even though the market seems to suggest that 600 bar could be enough, we wanted to make sure as part of this project and also to kind of explain to people why we don't recommend going higher. We also identified different spray hole sizes to find the optimal trade-off between low oil pressure, which gives you a longer component lifetime, less wear, lower cost, lower pump power consumption, and also increasing oil pressure. Normally in diesel operation would give you finer atomization and a benefit on combustion, and of course a smaller size is achievable. But on the other hand, we have to see if this what the trade-off is here for these new fuels compared to diesel. And for this reason, we created 3 different nozzles for alternative fuels. These ones with a beginning with A, and we compared the operation of the engine. We'll see later with these 3 nozzles compared to what we can obtain with a standard diesel nozzle, which was 8 holes with 0.33 millimeter diameter and rated for 180 megapascals. And you can see how the combination of reducing the pressure and also the lower heating value requires much bigger spray holes for delivering the same energy in the same time. So this was the framework for the hardware that we wanted to test on the engine. And we designed these different nozzles in a way that the injection rate shape at 3 different oil pressure levels would yield the same injection rate trace. And this was to be able to study just the effect of spray formation and decouple it from the injection rate characteristics of the injector. And of course, same injection rate, meaning opening and closing slopes, and also the same injection duration. So now, characterizing this injector on the test rig, we also wanted to check, the stability to lubricity, and so we ran for quite some time the injector with water with a little bit of ethylene glycol solution. And we, of course, also measured performance, and we could see that the performance in terms of injection rate is different for the 2 fuels, but that this is mainly due to the difference in density. And if we correct for density, we obtain basically the same injection rate characteristics, which means that we can also develop an injector using the standard calibration fluid like we did for diesel for many years, and we could get the right response in terms of dynamics. This is the same with the 2 fuels. It was not given for granted before, and it was verified in this example. And so, having identified these characteristics and well defined, we then moved on to characterize the spray of the methanol, in this case, the slides that I will show you, and compare it with the diesel spray obtained by the same injector, just changing the nozzle characteristics. We did this with the help of our friends at the CMT in Valencia in a non-reactive hot chamber, which means there was no combustion, but the gases were heated at the level of end of compression when injection should begin. And 2 setups were used to measure the vapor spray penetration with a Schlieren setup, basically looking at the shadow and variation in density fluctuations on the shadow of this laser source, and then also with direct illumination of the spray and MIE scattering to measure the evolution of the liquid spray. So for some results, we can see here on the left in colors are different rate pressures, and the dashed lines are the liquid spray penetration, and dashed lines are for the vapor spray. There is a cutoff at 75 millimeters, which is the size of the optical window of the equipment they have in CMT. So that's why this is, this flattening out is because it goes out of the measurement range. But interesting to see, first of all, with methanol, mainly because we have a lower boiling point, we have faster evaporation, so the liquid length is reduced, because then by then all the fuel has evaporated compared to diesel. And also, if you look at the slope of this, the speed of penetration of the spray, we calculate roughly 100 meters per second for the diesel, and only 70 meters per second with methanol. And this we can relate to the fact that also the spray is wider with methanol, so we have a wider cone angle. So there is more, in the end, also in the vapor spray, more momentum exchange with the air, and so we expect that with one hole we can cover a wider angle of the combustion chamber. So the qualitative take from this designs is most probably we need a reduced number of spray holes compared to the diesel equivalent. But this, we will come back to this when we look at the engine performance measurements. And also another interesting consideration is that if you also change the temperature of the gases in this spray chamber, we can see here that the continuous line is let's say methanol, and dashed line is diesel, and the red line is 50 degrees hotter than the green line. We can see that the liquid spray penetration on methanol is less effective than that of diesel to a change in temperature, and this again shows that this is due to the fact that evaporation is so facilitated with methanol that the temperature in the end has a lower impact on these characteristics with methanol compared to diesel. And then after all this, say, preliminary characterization and of course basic design validation, we went on the engine to try to find out how this stuff really burns and how we can make it burn in the best way. We did this at IDC on a 250 millimeter bore single cylinder engine at 750 RPM, the 17.1 compression ratio. And here we used the injector of OMT for two reasons. First of all, we fitted the diesel nozzle, and we used this for making a baseline performance measurement. And also we used this same injector, which has a capability of operating also as a pilot injector, to ignite port emitted fuel, in this case also gaseous ammonia, and I will show later some results. And then finally, most of the investigation was done with the nozzles suitable for new fuels and direct injection of methanol and ammonia. And in this case, we used the second small pilot injector on the side of the main one. And you can see here on the picture on the right how the two spray plumes interacted. So with this basic setup, we did some first measurements. For example, we compared a diesel combustion, and this is our baseline, is the red curve, to a 90% methanol, 10% pilot diesel setup having the same energy content. And we can see, going from the red to the black curve, that we have a lower peak of combustion heat release rate, and then a bit of a longer tail of the combustion process. But this is quite a bit influenced by the position in time of the pilot injection. So on the chart on the right, you can see that by starting the injection, the pilot injection very close to the methanol injection, like in the black curve, and progressively moving, anticipating the pilot, we can see the start of rate of heat release is sooner, because this is the energy coming from the pilot injection, and then we have let's say combustion evolution, and depending on the pilot, we can actually shape the rate of heat release quite a bit to get closer to the original one with diesel. Then this is rather qualitative, but if you want to look at the quantitative results, we can take, for example, a comparison of direct injection of methanol versus diesel with the same center of combustion at 10 degrees after the center and an excess ratio of 2. And we performed also a variation of dwell time, which is the difference in time between the start of the pilot injection and start of the main. And we got this results in terms of trade-off. And we compare them with this baseline, which is the green dot, obtained with diesel at 160 megapascals of injection pressure. And here we have the equivalent operating points of the engine for 640 and 840 megapascals with methanol, respectively. And the arrows indicate the increase of dwell time. So basically, anticipation of the pilot shot compared to the main methanol injection. So interesting things we found in this investigation is that actually, if you get around 640 bar, we get a better trade-off, both in terms of fuel consumption and NOx emissions, and that the sensitivity to dwell time is not so big. While when we increase the injection pressure, we could lower the fuel consumption, but changing dwell time rapidly increased it again. And also we would move already in an area where the NOx emission would be higher than at lower pressure. Now, looking a bit on the dark side of this, first tests, we have a worse hydrocarbon emission compared to the baseline in diesel, which means that most probably we needed to increase the excess air ratio and possibly look at a different nozzle spray configuration. I was anticipating that we have a wider diffusion angle of the spray. So the hypothesis here is that we have areas of overlapping sprays, and that's causing some areas of not complete combustion. So that's, let's say, the starting point for further tests that we will do to get to the bottom of it. But we can see the potential of not just burning, fuels that promote reduction of greenhouse gas emissions, but also there is a potential for optimization of the engine as a whole. As a closing point, I reported the first result we obtained with a completely different concept with 14 admission of ammonia and using the OMT injector as a diesel pilot system, with going from progressively higher substitution rates from starting the engine 100% diesel and then starting to add ammonia to the intake manifold and reducing of the same energy quantity the amount of diesel injection. How initially we have an even faster a higher peak and a bit faster combustion. But then when the ammonia gets 60% or so, then we have quite a big tail, and it looks like there is a limit in trying to push this the combustion of ported emitted ammonia without highly, say, detrimental effects in terms of incomplete combustion and pollutant emissions. So this was what we did to test later on the direct injection of ammonia on the same engine. We had some issues with the fuel system that is now being checked, and that's why I could not report yet injection operation with ammonia, because it could not be supplied adequately yet. But let's say the story goes on, and we will hopefully present this at the next CIMAC Congress in Busan in June next year. So just some conclusions of this in progress work. We designed an injector suitable for testing the pros and cons and pitfalls of operating with these new fuels and understanding where the critical points are. We showed that we can characterize the injector also using calibration fuel for performance optimization. Spray analysis gave us some interesting insights, like with methanol we have a shorter liquid spray length due to faster evaporation, and also we have a wider vapor spray angle and lower penetration speed. And on the engine, it seems like we can get a better overall trade-off, in terms of both fuel consumption and NOx compared to diesel. At the moment, we had higher hydrocarbon emissions that we need to work on to complete the picture and give a reliable overall comparison of the two fuels operating on the same engine. And then another take from this first test is that there doesn't seem to be much of an advantage in going high in pressure with methanol, let's say above 600 and something bar. Also, we kind of found out that injecting pilot and main more or less the same time gives probably the best trade-off that we could find at the moment. And as I said, this work is still in progress, so stay tuned, and I hope to see you all and more in Busan next year. Thanks very much.
Okay, thank you so much for preparing this very, very interesting presentation for us and sharing the results with us. Thank you. Impressive. And as I cannot see a question on the board right now, maybe let me address one question. You mentioned that you are prepared for quite high injection pressures, up to maybe 1500 bar, and you already investigated injection pressures the range of 600, 800, and even more. What do you think out of the very first results? Where does it go? Does it make sense to even increase? Can we not tell this right now due to the NOx emissions? What's your opinion on that? Also, you're not for combustion development.
Thanks very much for the question, Michael. Of course, the situation is complex, and we need to dig deeper into it. But for sure, the fact we demonstrated that the methanol evaporation is let's say not an issue when the chamber is very hot. It might be an issue if you have a port injection due to the high heat of evaporation of methanol. But when we are at the end of compression stroke, the temperature is so high that methanol seems to evaporate well and fast, and so the spray, the pressure that normally you need to give momentum to diesel to break it up and to make it go far maybe you don't need to have so much momentum, because then the breakup occurs almost by flushing the fuel, and then the mixing between fuel and air is facilitated by this methanol characteristics. So for sure, I would not say we need to go to 1500 bar, even though some customers are trying to do that. And I'm saying this because also on the pumping equipment and anywhere when you have a high flow velocity with the pressurization, sudden depressurization of the fuel, then you have the risk of cavitation erosion, and so so we might also have a trade-off between excellent performance and also durability.
Sure. Thanks, Marco. I can see two more questions now on the board. One is about at the engine test of DI methanol, micropilot was injected with the same injector of main injection of methanol, or by separated sub-injector? So that's the question.
Okay, so here there was a bit of confusion because we used the main injector for both when it was in diesel, but let's say when we are running with alternative fuel, let's say imagine the methanol spray is this blue one, and then in this case for ignition we use a separate injector with the spray pattern of that is represented here in orange. So that the injector is a single nozzle one, so it can only inject one fuel at a time in this configuration. But when it's in diesel mode, it can go down to 0.5 to 1% of maximum. So you can also use the main injector operating in diesel mode as a pilot injection provider for, in this case, a fuel that is admitted in the port, because of course there is no other way of introducing it in the combustion chamber.
To be more precise, the question was: is there a difference in nozzle hole between the pilot and the main injector, as far as I get this question? Let me see. No, I guess the question is already answered. Yeah. Thank you. There's another question. The firing pressure of different fuels for same power output.
Okay, so the question is, how does the compression pressure and I'm not sure of the question.
Yeah, me either.
Okay.
So maybe you can more precise with this question, please. The question was firing pressure of different fuels for same power output. Okay. Marco, if you do not have an idea.
Okay, so I would say, I guess it says if the engine is going to be stressed in a different way if we use a different fuel. I think the idea is that we, as I showed at the beginning, we try to deliver the same, say, chemical energy input for the diesel and for the other alternative fuels. So that means we have to have a different mass flow rate of alternative fuels because they have a lower heating value, but then the goal is to introduce the same energy. So in the end, if we have the same compression pressure and we have the same energy input, I would expect that we are targeting for a same peak firing pressure. Yeah. So not to stress the engine in a different way. That would be the key. Then we can play with different modes. But initially, the idea is to, and also because we are looking at a world that is full of diesel engines, and we want to also be able to retrofit that we try to get good operation with the same mechanics that we have available, so that we, in principle, I would not start changing the peak firing pressure.
Mm-hmm.
I
Yeah,
hope
looking
that
at the
answers.
yeah, sure, Marco. Looking at the peak firing pressure, that makes perfectly sense. Sure.
Yeah.
Okay, let me see if there's another question on board. No, it is, and we are perfectly on time. Thanks again, Marco, for your presentation. And I will lead over to Gunther. Gunther Hager is from Mibo Gleitlager Austria, and he will talk about joint development of the bearing system for AVL's new high-speed engine platform. Gunther, please.
Yeah. Good afternoon from my side. First of all, let's get the presentation started. Is this already working? Do you see the screen already?
Yes.
Okay, then let's get started here. So, okay, sorry, this is not the one. Sorry. Yeah. So good afternoon again from my side. My name is Gunther Hager. I'm working for Mibo now for around about 12 years, but I also have a background with AVL. And this work, the crank train development of the AVL high-speed large engine platform, has been supported by AVL, especially Mr. Rustler, Mr. Flesch, and Mr. Estebanes. Yeah, first of all, to the content. So I will show, or I will introduce the motivation of these projects. There will be an introduction of the whole large engine platform. I will talk about the lead-free portfolio from Mibo and the introduction of our big end bearing monitoring system. There will be some intermediate project highlights. So we are talking about the results of the first testing campaign on a single cylinder engine, and also some verification and validation between measurement and correlation to the single cylinder engine results. And of course, at the end, there will be a status outlook, target achievement, and what is coming next in the testing campaign in the Q4 2022. What is the specific motivation? The ICE will also in the future play a major role for transport and power supply. And of course, reliability is a major point, and this will not change despite alternate fuels are popping up, as already explained by the lectures before. Therefore, it makes much sense to further develop the ICE, but not only the thermodynamics, but also looking at the whole crank train, looking at maximum efficiency, but also the compatibility to renewable fuels is important. And also we have to have a look on the regulations. On the one hand, of course, emissions, but also materials that are used within the engines. We are talking here about thermal efficiency and reduction of friction power losses. Of course, we need a robust powertrain in combination with new bearing solution, especially when we talk about hazardous materials as lead. Of course, we are looking at enhanced simulation methods to have a first-time right approach, and also to improve the development efficiency. And what is also key for future is to have a reliable monitoring system for verification, but also for health monitoring. This project what was not done by AVL and Mibo alone. There were several supporters and project partners as named here as Tenneco, Kolpenschmidt, Märkisches Werk. And the project was funded by the COMET framework and was done, the single cylinder engine tests were done on the Large Engine Competence Center within the Avrp program. Let's come to the basic AVL large engine platform. We are talking here about a 175 millimeter bore engine with a stroke of 250 millimeter. We see some rendered pictures here of the single cylinder setup. The engine speed is typical for this engine size between 1500 and 1800 RPM. And one major goal was to achieve a peak firing pressure around or above 330 bar, meaning a brake mean effective pressure of 35 bar. The specific fuel consumption should be below 165 gram per kilowatt hour, and it was a target to gain an efficiency of above or around about 51% in the gas mode. Of course, minimized lube oil consumption is a must with these boundary conditions. Several combustion concepts were tested or were and will be tested. Diesel direct injection, active pre-chamber spark ignition concept, and passive pre-chamber spark ignition with gas, direct injection with hydrogen, and port injection with hydrogen. Coming to the technological overview, more from a mechanical point of view, there has been a new patented cylinder head cooling and strength optimization concept and a patented crankcase cooling. Of course, all these features have been simulated using CFD and multi-body dynamics, as well as finite element analysis. The cylinder distance has been optimized, and this concept is not only done for the single cylinder, but in the background there is already a V20 concept that is based on the single cylinder setup. In addition, the valve train has been optimized for maximum stiffness, and one major key feature on the whole engine was to optimize especially the conrod small end to avoid need of active lubrication, also for manufacturing reasons. Let's switch over from the AVL large engine platform to Mibo's future bearing portfolio. So you see here the copper-based lead-free portfolio. Maybe I do the laser pointing. And here you see the portfolio on the one hand of the half shells as well on the bushing side. So we will have in the future a Syntec and especially two sputter options on a lead-free basis. And we will have, beside as an option, there will be also electroplated version, and we will have for the small and also a lead-free version, a pure bimetal as well as a electroplated coating bearings. These three bearing types have already been tested on the single cylinder engine, and I will show some results in a minute. All in all, Mibo will provide a consistent lead-free portfolio within end of 2022 to be ready for production and serial deliveries. What is the lead-free solution all about? We see here a short overview of the pros and cons of the different base materials. So on the one hand here we see the characteristic of the standard leaded bronze with quite good tribological aspects, and also the castability and the machinability is very good. We had in the past a intermediate solution of the lead-free. We call it here the Gen 1, but these had some basic disadvantage, especially from the machining, but also from the robustness and tribology. The next step, and this is the actual development and also been tested as said before, this is the Gen 2, where some sulfur content is within the bronze that especially improves dramatically the machining capabilities, but also, and this is important for the robustness of the whole engine, has major improvements on the robustness. There have been tests also on our rigs, and you see here a standard seizure load test program and the results. And we see here again the three bearing type, the basic bearing type. So we are talking here about a bimetal bearing without the coating. So the first one, again, this is the seizure load result of our lead bronze as a reference. Then we see and mentioned here in red that the Gen 1 lead-free bronze had some major disadvantage on the seizure load, but with the generation 2, it's internally called Inno alloy, we are more or less on the same level from the seizure load result compared to our reference, the leaded bronze. Coming to the second feature that is introduced in this engine is the monitoring system for the big end bearing. We see here the connecting rod of the single cylinder engine, and here we have a telemetric unit that is mounted on the lower part of the connecting rod, and this is not driven by a battery, but with an inductive system, and with the mounting of a magnet on the crankshaft, or let's say the web or counterweight, this depends on the design, we get enough power to reliably drive the system. To get the temperature result from very close to the bearing, we machine the bearings on the side, drill some holes where we get some temperature information down to 50 millimeter to the middle, and only have to machine a small slot on the side face of the connecting rod to get access to the measurement position. All other machining is originally as done without any additional machining. With this system and the energy we have a receiver unit that is somewhere mounted on the crankcase, and with this receiver unit we have a connection to the engine control and application monitoring. Showing one slide about the design here. So on the left side you see here the actual CAD model of the prototype, and as we had some design restriction, we had to mount this magnet holder on the side, but we already had a look at different designs on a multi-cylinder engine, and in most of the engine it is possible to mount this magnet that has to be used to drive the system underneath the counter, kind of plate that could be assembled together with the counterweight. Coming to the initial validation of the single cylinder engine. So from the cylinder head and the valve seats, the structure and cooling, everything was working perfectly. So there were no issues on the whole system. Everything was working well, and so no need to do any changes. And the preparation on the CRE side worked perfectly. The same for the piston and the liner. So there were no issues on the cooling gallery. The skirt profile was fitting, and also the liner and the running surface looked perfect after the first tests. Coming to the conrod. So the conrod, we see here two pictures of the big end bearing and the small end bushing. So especially on the small end bushing, there were no specific edge loaded visible after these tests. And I will come to that on the next slide, how this has been achieved. Also for the big end bearing, the running pattern after the first 100 hours were looking perfect. This is only discoloration with the tin antimony bearing that has been used for the first break-in of the engine. And this is a very uniform running pattern without any major issues. How has this been achieved, especially by using of CIE, especially on the single cylinder design, the virtual development. So the whole layout has been done as also described in the introduction, for a system unit capable of achieving a peak firing pressure of 330 bar. The micro and macro geometry has been defined using all the CIE methods, being AVL, Excite, be it post-processing and further processing with finite element models. And EHD has been done for both the big end and the small end to define the bushing dimensions and the shape. Of course, based on that, there was a clear proposal of the machining according the proposal by using the CIE methods. And therefore, we did not see any specific break-in wear during the engine runs as shown in the slide before. What also has been tested and worked perfectly on the small end bushing, no direct feed of this pressurized oil supply was used. So there is no feed bore between the big end and the small end. So the engine on the small end works similar as known from smaller engines as truck size. Yeah, to some detailed result out of the engineering. On the left side here, this is the design of the small end bushing, and we see here the distribution of the maximum pressure in megapascal. And of course, we see also from the asperity, in this case, for maximum power output at 1,800 RPM. And beside the total pressure, it's also depicted here the asperity contact pressure. And as you can, yeah, it's not so easy to visible, but as shown here, of course, there was some initial edge loading, but this edge loading can be corrected by a virtual running in procedure, which gives the final shape of the inner surface contour of the bushing. And as already shown before, the result fits perfectly. So this shape correction, no specific polishing has been seen on this bearing type, lead-free bearing type bushing provided by Mibo, without any coating to be mentioned here. So it's a pure steel lead-free bushing solution. On the big end, same, and this is pretty standard, EHD simulation has been done, where we see the total pressure distribution on this picture here, and only very minor asperity contact pressure. So the design was optimized so that the asperity contact pressure can be minimized, and no other corrections were needed. So we could, as Mibo, we could use a standard bearing layout for the validation. As shown before, we see here the bearing that has been used for the break-in procedure. This is a steel lead-free bronze and a soft sputter layer, because the first running in of an engine is sometimes always critical, because you don't know what will happen on the first start. Therefore, we decided to use a soft sputter layer, and later on, after 50 to 100 hours, the bearing has been exchanged by the so-called Mibo 6G type. This is the aluminum tin 20 sputter with a synthetic overlay. You see it here in black. And basically also the appearance was pretty perfect. Yeah, we see here some scratches to some small particles that are going through the synthetic layer, and therefore we see the gray shiny aluminum tin 20 sputter underneath. But besides that, the running pattern was perfect and no issues have been detected after the assembly. Yeah, coming to the results on the telemetric unit. So we see here on the right side the de-assembled power unit with the connecting rod and the explained telemetric system. Yeah, here the piston pin and the piston. And on the left side here, there is a part of some recorder time measurement results. And in green, we see the brake mean effective pressure with up to more than 30 bar, 35 bar. We see in blue the engine speed, and we see here two of the results of the temperature measurement of the big ends. Yeah, we see some single outliers. This has to be will have to be corrected in the future with some electronic modification or some post-processing. What is very important here is also under the very high loads, we see absolutely no specific impact on the temperature on the big end bearing. So after braking, the bearing works perfectly in hydrodynamic mode. There is a perfect stabilization of the temperature, and what has also been expected, if this is the case, the load has only a minor impact on the temperature. More important is the engine speed. As we see here, we have a pretty constant temperatures. When the speed is dropped, we see an immediate impact on the temperatures, and of course, if it's stopped, then of course the temperature drops as well. Yeah, in total, we can say that our system is running down to a speed of 800 RPM. We got reliable temperature measurements up to 250. I think in the meantime, it's more than 300 operating hours that have been done on the system. So everything's working well for these first testing campaigns. Coming to the outlook and the status. So all the intermediate target results have been achieved. So the brake mean effective pressure, the peak firing pressure in diesel and gas mode have been achieved. The mechanical development didn't show any signs of weakness, be it the liner, the piston, the cylinder head, but also the power unit with the connecting rod and the big and small end on the connecting rod. So from this point, there are no issues to further progress with the project. There is a testing campaign planned or already in progress. Maybe Michael can tell us news about that in Q4 2022. There will be some heavy instrumented components that have not been used until now, especially on the piston, the liner, and the cylinder head, the seat and seat rings. So there will be much more measurement data available after the end of the testing campaign. There will be some additional testing on the big end bearing system for robustness reason. As it has been designed there is a separate supply line for the big end bearing, and there will be some robustness tests with variations of the feed pressure and the oil flow volume. This is of course only possible with a monitoring system to not risk any engine damage. And of course, last but not least, a very important topic, of course, developments from the combustion side using alternative fuels. That means especially ammonia and methanols will be used. I think I didn't mention in the presentation, also hydrogen injection will be tested. There will be combustion development on these fuels, and of course what is very important as well, especially in the interaction between the bearing and the lubricant, some sensitivity investigations will be done. Yeah, and last but not least, of course, a result validation and the final reporting will be internally available within the first quarter of 2023. So I'm at the end of my presentation and waiting for questions.
Gunther, thank you so much for giving us an insight of the development phase of this high-speed engine platform. And I'm looking at the board. I cannot see any questions so far. Let me address one question. You talked about the bearing temperature measurement with the telemetry system. And of course, it makes sense with this high speed, high load engine up to more than 30 bar BMEP. Can you think of other applications where it would make sense beside research and development, such a monitoring system?
Yeah, basically we didn't design the system only for development. So as we are supplier of parts, we think that midterm, of course, it could also be possible to use such a system for serial application. Of course, the development also is not finished. Yeah, so they are in the moment. We only did five different tests with different customers, not only on the AVL engine, but also with some other customers. And there are still some smaller obstacles, but generally it could be used also for serial application. We also scaled it down, so generally it's also usable down to a truck engine size. This is for this system the limit. Our major target is this engine segment at the bore between 160 and let's say 250 millimeter.
Mm-hmm. Yeah, thank you. Yeah, there's no question on the board. One more question, Gunther, maybe. Do you already have experience? Today we are talking much about methanol and ammonia, so alternative fuels. What is the, in terms of resistance to your bearings, do you have experience with that already, or are we looking forward to further engine tests with alternative fuels?
On the one hand, we need more engine tests also to see the interaction between the fuel and or the combustion products that will partly will touch, let's say, the lubrication system. Also kind of with blow-by, there is also a little bit of ingress in the lubrication system. And of course, we are dependent on engine testing. This is the one thing. But of course, we are also cooperating with partners who are who will provide additive systems to avoid formation of acidics, because we know from the past that it might harm the bearing system, and of course we want to avoid that switching over to alternative fuels. But of course we are at the beginning there. So
Yeah.
it's a major step for us to do this development with AVL, but also with other OEMs, doing some developments, testing system, testing lubrications, and also maybe artificially age the lubricant by some ingress of these fuels. All these things will be needed so that we have a reliable system in the future.
Yeah, thank you, Gunther. I totally agree. So it is, of course, about the lubricants and the combustion products. What will be going on the bearings? Sure. Thanks. Yeah, with that, we're perfectly on time. I will hand over. I will give the word back to Mark. Thanks for preparing the presentation. Thanks for joining. And Mark, please take over.
Yes, thank you very much for guiding us through the day, Mr. Engelmeyer, and thank you very much to our speakers for the interesting presentation. And today I also want to use the opportunity and say goodbye to our audience and all our speakers. And I am, of course, looking forward to seeing all of you at the Congress in Busan in 2023, because with today's Tech Talk, the series of Tech Talks is going to end. And we hopefully prepared a nice warm-up for all of you so that the waiting time for the postponed Congress isn't too long. And that's all I wanted to say. So see you all in Busan and have a good day. Goodbye.
Bye-bye. See you later. Bye-bye.